Hi, let's look at the Y connection and the delta connection for the load, for the three-phase balanced load. So you may ask the question, why do we need one connection over the other? I actually had one concrete example in the real world, and many years ago I used to work with Carrier, the air conditioning company, and the company produced the very large chillers. Those are driven by the very large motors, the three-phase electric machines. And those three-phase electric machines, normal operating condition is the three-phase windings, they are connected in delta. Okay, and but during the start, there's the contact. There's contacts you can reconnect the one to the Y connection. And for the Y connection, the electric machines will draw less current, because when you start, you draw a large amount of current, and the whole building, maybe you get a voltage dip, right? That's what happens if you, because the electric machine, when you start, they normally draw the higher current. You may have similar experience when you turn on your the sink disposal, right? These little single-phase motors, when they start, they have they need to draw a large current to get the motor spin. Once motor starts spinning, and they draw less current, and so when you just start, you see the light bulbs around your kitchen maybe just dip, right? Because they draw more large current, and the voltage drop across the line. The line has a little line impedance, right? The voltage drop across this line impedance from whatever the incoming feed and your house to your kitchen sink. So that voltage drop becomes bigger. So therefore, the voltage at your the load point is getting lower, right? So that's the reason. And so for the three-phase large electric machines, they use the Y connection to start the motor. After the motor speed reaches a certain point, so the controller will switch that back to, and typically done by the timer. So after a number of seconds, they know the motor speed is almost up, so you can switch it back to the delta connection. Actually, it was quite impressive because you hear the sound, the clicking sound, and also the kind of spark stuff like that. Because that's a few hundred kilowatts motor. Okay. In this context, we're gonna see the two different connections, and for this course purposes, and if you have a delta connected load, and typically is more complicated to analyze unless we can convert that to the equivalent of Y connection. Okay, so we did a Y and delta connection in 201, I believe, but that's for the resistance, because each of the impedance, the resistance is not the same, right? So that will be more complicated. But in the three-phase balanced, the three impedance in each phase will be the same. So the equivalence actually is much easier to establish. Let's see the equivalent impedance for the Y connected load. I have the Z sub EQ1. So this is the equivalent impedance looking from the pair of nodes A and B, while leaving this the third phase, this open circuited. And so that means the third line is not connected to anything. If we do the equivalent impedance Z sub EQ1, apparently that's just equal the sum of this ZY plus ZY, right? So that's going to be equal. To ZY, right? And for the delta connected node, let's see, we're also looking into the pair of nodes A prime and B prime, and so and also leaving the third phase open circuited, and that means that's not connected to anything. And then in this case, the ZEQ2 is going to be equal to, so I have this impedance, right, in parallel with the sum of these two. Because these two now, they are in series because this one is not, this line has zero current, right? So therefore, I have ZEQ2 is going to be equal Z delta in parallel with 2 Z delta. And if you remember the parallel impedance, this is the product over the sum, right? So therefore that's equal Z delta times 2 Z delta divided by the sum, or Z delta plus 2 Z delta. And Z delta definitely can be cancelled one of these. Let's see, cancel one of these. So I got a 3 on the denominator, I got a 2, so I got a 2/3 of Z delta, right? So for these two connections to be equivalent, we have to have ZEQ 1 equal to ZEQ2, and therefore that will give us the 2 ZY is equal to 2/3 Z delta, and that requires ZY is equal to third. That equals the third Z delta. So this is the condition for this being equivalent. Let's see if you have the three-phase delta connected load, and if you want to convert to Y, you just divide by that impedance by 3, and you redraw the circuit. Okay, and this will simplify the calculations. So let's see the example. Very simple example here. I have the three-phase balanced load, balanced circuit with a positive sequence, and now the load is delta connected, right? So that we have Z delta given, and I'm trying to find the line currents. You could do is to find these currents and try to find the IA by adding this current. So that will take a little bit longer time. So what I do is I just replace this by ZY, right? So if I replace this by Y connection, so the ZY, and then I can do the single phase equivalent circuit, right? So I can do the single phase equivalent circuit, and this one I don't really have any line impedance to simplify this the problem. And so I have VAN, and that's just VIA, right? So I can calculate IA very easily. So IA is going to be equal to, and by the way, ZY, we know ZY should be equal a third of Z delta, and that's, I think that I have 6 plus J9, so I put the number to the 3J, right? This many ohms, and so therefore the IA is going to be equal to VAN divided by ZY, and I calculate the numbers beforehand. So let me get that number. That's actually is equal 76.8. The phase angle is negative 56.3 degrees. Of course, that's RMS value, right? And I can the IB is going to be, I don't need to calculate. I know this is a positive sequence. That means IB is lagging IE with the same magnitude. Lagging IA by 120 degrees, so minus 120, that should be 176.3 degrees, right? And the IC is going to be equal to the 76.8, and then that's a plus 120, so that's a negative 56.3 plus 120 degrees, and the RMS value. And then to calculate the actual number. The number is 63.7, and the RMS value. Okay, so if you calculate the three-phase, that's the same deal to calculate the three-phase. You can use ZY to calculate the three-phase if you ask to. So the three-phase current, the power, complex power is going to be the IA magnitude square times ZY multiplied by 3, right? So if you ask it, so we didn't ask this in the problem. If you ask it, you can use the equivalent impedance. So the impedance equivalent, that means that all the voltage, current, power all equivalent to the original circuit. Okay, so that's the Y and delta connection. I know some of you think about Y and delta connection is really boring for in the electrical engineering. I don't think so, because this really, in the real world, you have electric machines connected either in delta, in Y, or you have the transformers connected in delta and Y. And when you take the course, some of you may take the course 423, the power system, and these very practical situations, right? So that's not just an academic exercise. I hope you enjoyed the videos, and so we will have one more video to cover for this course. Until next time, remember, no matter what you do, just keep going, right? So I'll see you next time.